So our next session, similar to this morning, we have a series of highlight talks. So again, these are three leaders in the field of robotics who will be giving a lightning talk style speech. I will introduce all three speakers at once, and then after each one, they will just come up for their turn. So our first speaker will actually be remote. It is Professor Dieter Fox from the Allen School of Computer Science and Engineering at the University of Washington. He is currently splitting his time between UW and NVIDIA, where he is leading the Robotics Research Lab up in Seattle. Next, we will hear from Professor Lydia Kavraki. Professor Kavraki is the Kenneth and Audrey Kennedy Professor of Computing and a Professor of Computer Science, Electrical and Computer Engineering, Mechanical Engineering, and Bioengineering at Rice University. She's also the director of the Ken Kennedy Institute, and in this role, she brings together faculty across all 7 schools and multiple departments to shape large research projects and future directions in AI, data, and computing. And her research spans robotics, computational, biomedicine, and physical AI. And then our last speaker of the segment will be Professor Monroe Kennedy. Professor Kennedy is an assistant professor of mechanical engineering and a courtesy appointment in computer science here at Stanford, and he directs the Assistive Robotics and Manipulation Lab, focusing on enhancing robotic autonomy and effectiveness in human-robot collaboration, integrating machine learning, computer vision, state estimation, control theory, and motion planning. So first, we will hear from Dieter.
Hi, everybody. Thanks so much for inviting me to give this presentation. Today, I want to talk about hierarchical action models for open world robot manipulation. This is joint work between NVIDIA, University of Washington, and USC. So one open question right now is how can we in robotics, how can we leverage these extremely powerful vision language models for robot manipulation? And one paradigm that we've seen recently evolve more and more and come up is hierarchical ideas where we combine, for example, a vision language action model with low-level control policies that can be executed on a robot. Examples for that are, for example, the recent work on HiRobot, Gemini Robotics, and our own hamster work that I'm going to present today. So the idea here is that at the higher level, we have a vision language model that takes as input, for example, text, images, and the task the robot should execute. And it generates some kind of interface, some kind of context for a lower level model that then performs control policies on the robot. And this interface layer, which means how the high level model communicates information to the low level model, is still an open area of research. You could imagine this could be latent codes, embeddings, trajectories, bounding boxes. And in this specific line of work, we pursue 2D trajectory sketches that are generated by the high-level models. The advantage of this hierarchical approach here is that the high-level model can really be trained at internet scale. It doesn't have to do complicated fine-grained 3D reasoning, and therefore can leverage all the data that is available for training. And then this trajectory sketch is being used by the lower level model, which is a 3D policy that, for example, might use point cloud data in order to produce more fine-grained motion control for the robot manipulator. And this policy also uses the 2D trajectory sketch in order to generalize and get more guidance from the high-level model about what specific objects, for example, it should interact with. Let me just give you an overview of the system here, where imagine you have the task of the robot should pick up the block with the M and put it on Mona Lisa. Then first we train and fine-tune on VLM to generate this trajectory output, which are 2D image coordinates that specify, for example, in this case, where the robot should move the gripper and then close it, which is on the left image here, this blue circle. Next is an intermediate trajectory point. And finally, for example, where it should move the gripper at the end and then open it to release the object. So this is the level of the high-level model, which performs semantic reasoning and generates these intermediate trajectory points. We can then use these in order to generate in the image space dense 2D trajectories, where the color along the trajectory is kind of like a timeline. And in order to feed this into a lower level 3D policy, we're going to add also depth image data to the input. And we're going to rewrite the input task in a more generic way that just says pick up an object and place it somewhere, where now the lower level policy needs to learn to interpret the 2D trajectory in order to figure out like which is the object to pick up and which is the object, for example, where should it place that. We can now feed in all that information into the low level policy that turns it into an actual motion commands. Okay, so now let me give you a bit more information on how we train the high level model for this and also then the low level policy. On the high level, we are in this work, we are leveraging VLA, which is an open model developed by NVIDIA, but you could imagine fine-tuning any other capable vision language model to do this task. And the key ingredients for the fine-tuning is really these robot trajectories that we're generating. And we're using for this data from Bridge and Droid. These are real robot demonstration data sets. And you can see here on the left, for example, from the Bridge data set, where the robot picks up a green object, puts it in the silver bowl. And we can automatically extract from that data set the gripper trajectory that you can see now here down here, indicated by this colored 2D line on the image. Same here for another task like fold the towel. And we can also do this, for example, leveraging our L-bench data set, where we can also take various tasks like opening drawers, pushing buttons, and from those we can generate these target outputs, these 2D trajectories in the images. Have in mind that at this point, we're not training any real policy here. We're really just fine-tuning the VLM to generate the output that can be provided for these 2D trajectories that you see on the lower images. So that's the only purpose of this kind of data. Out of this fine-tuning step, we're then getting actually a very capable reasoning system that we were actually surprised about how well this works. So for example, here you can see something like move the S to the plate the arrow is pointing at, which is kind of not an immediate just object identification task. And you can see the trajectory correctly identified that this is a red plate. If we present the same image to the VLA and say move the S to the plate the arrow is not pointing at, then that actually correctly identified that it should go to the green plate. Another interesting aspect that we're getting out of this high-level model is, for example, that there's a task here like this one, screw the light bulb in the lamp, that we have only training data in our L-bench, the simulation training data, which you can see the rendering here is not very high quality, but the model then can actually transfer very well and can be applied on real-world images. Here, let me give you another example. There's the push button task, which is also only in the RL bench data set in simulation. And the model then is able actually to correctly interpret this task here, where it has to identify which of the two red buttons is the big one. And interestingly also, for example, in the training data, these buttons were only identified by colors like red, blue, and green, but it can transfer that even if, for example, the green button is identified through the color of leaf. So these are all kind of these transfers and generalizations that we're getting automatically by fine-tuning a very capable vision language model. Another interesting aspect here is, for example, camera viewpoint independence and robustness to that. So here's, for example, pick up the M&M chocolate and put it in the yellow mug. And what I'll show you here is kind of this drawing of the trajectory that the model outputs. Even if we change, for example, the camera viewpoint, you can see that it's actually pretty consistent across all these different viewpoints, which is this kind of robustness that, of course, we want to have from this kind of robotic reasoning where a robot might approach the scene from many different viewpoints. So now that we have the high-level model trained, the next question is on the low-level model. How do we train the 3D policy? In this case, we actually tried out two different low-level policies. There's RVT2 and 3D diffuser actor. We could also use other diffusion policies, but these are the two we tried in the hamster model here. And to train these lower-level policies, we generated 320 examples, not more, of tasks like pick up an object, place it somewhere, or press these buttons. And also here on the lower left, for example, topple over an object. In order to see the generalization of these policies, we can then change, for example, certain settings between train and test data. So for example, we can change out different objects. We use different ways to refer to objects, spatial names or object identifiers, and also even change the background and things like that. So on this slide, you can see the results if we now test these policies across different variations that we might make. I'm sure I don't have time to go into any of the real details here, but for example, here are changes where we change, for example, you can see in the lower left, we might change the background of the table, we add objects to the scene, or we change like how we refer to an object and how we identify buttons to be pressed. And what you see here is for RVT2 and 3DDA, these are kind of the results we are getting across these changes on the test scenes. And you can see that the results are not very strong. We also, as a baseline, trained OpenVLA on these tasks. So again, we fine-tuned OpenVLA on these 320 examples, and these are now the results we're getting on the test cases. You can see that we're getting quite some robustness out of leveraging OpenVLA's more general reasoning capabilities. But most interestingly, this is now what we're getting out of the hamster model. In this case, if we combine hamster either with RVT2 or 3DDA, and you can see that the results are significantly better than any of these alternatives. And it really kind of highlights the power of combining the high-level semantic reasoning that we're getting from a VLA together with the lower-level 3D policy reasoning that we're getting from these other trained models. Let me just briefly, here's just some example of different kind of tasks we are doing here on the test cases. These are kind of quite 3D tasks, right? So for example, putting objects into shelves and things like that. Here's another very quick last example. We can also kind of have a kind of conversation, of course, with the model, and then pick up a crushed can, put it, and we can do this kind of task with the trained model then. And again, leveraging both the semantic reasoning power, open world power from the VLA, and also leveraging the 3D motion policies that we train. So with that, I want to summarize. I think it's fair to say that these VLMs are becoming just more and more powerful on open world reasoning, but also on fine-grained visual tasks. With just a little bit of fine-tuning on more manipulation relevant outputs, in this case 2D visual trajectories, for example, we can generate VLAs that have very strong semantic and spatial understanding of manipulation tasks. We're getting very good sim-to-real transfer at that level. But at the same time, it has to be said that these VLAs are not quite high frequency enough and not reactive enough to be deployed in for robot manipulation settings. They're also not precise enough for the 3D motion that we need for robot manipulation, and also more higher dimensional dexterous manipulation tasks. That is where these hierarchical VLAs come in, which I think then leverage the capabilities both of the open world reasoning and reactive motion generation that you get from these lower level policies. And I think moving forward, I think the key open steps is really on improving the lower level motion policies. I think these VLAs on the high level reasoning are already extremely powerful, and we're going to see more progress. But I think where we really have to move more is train lower level policies on far more data, as we're seeing, for example, by Physical Intelligence and other companies. so that we get more robust 3D policies. And also this interface between the high level and low level 2D trajectories is just an initial example. I think there's going to be much more powerful interfaces, for example, through latent encodings and alternatives, and that is a direction for very exciting research moving forward. And with that, I'd like to thank all the authors on this work, and especially I want to highlight the project lead, Yi Li, here on the upper left. He's just finishing up his PhD. He's on the job market. So if you're looking for a great research scientist, get in touch with me. I can make a connection with him. And with that, I thank you for your attention. Thank you very much.
Good afternoon. I hope you have enjoyed this conference as much as I have today. I feel I've learned a lot. I'm going to use my time to talk about task and motion planning, work that is going on in my group for many years on this topic, but also share broadly my thoughts on this topic. So clearly, we've all understood that there is an explosion in the interest and the work that is going on in robotics today. And this, many years ago, we just wanted to move from A to B. Now we are talking about generalist robots that will go into my home, your home, and will perform interesting tasks. And this growth is trailing a little bit, but I think also is inspired by the successes that have been happening in AI broadly, but more specifically generative AI. So as you've heard today, we have amazing efforts in the community to collect data for training models. We've all understood that it's different to train a model for a robot and different to train a language model. So I'm referring to the Droid data set, for example, the OpenX embodiment. These are amazing efforts by the community to collect data. Also, let me point out the use of simulation. Simulators are becoming much more powerful than they used to be, and they are closing the sim-to-real gap. I've also seen a lot of work on blending data collection, physical data collection and simulation. So it is very interesting what is going on. And there are many new companies and many research institutes working on this topic. And I think we have to pay attention and understand what are the capabilities and what are the limitations of this work. But definitely you will agree with me that it's a lot of effort, a lot of compute, a lot of money, and a lot of time that is going into this effort. So what I want to do is I want to bring your attention to some other issues that I believe are very important for making progress and having robots that are capable to help us and to augment our capabilities. So I want to talk about the power of having robust core operations. For me, a core operation is motion planning. I've been working in this area for many years. But it could be grasping. It could be pushing. It could be compliant motion. I mean, there are many core operations that if we make them really good and really robust, I think it will help. Then I want to talk about the power of abstraction, modularity, and composition. Compositionality, in my opinion, of operation is something that is critical for achieving long horizon tasks. And then I will say a few things about putting the human in the loop. So let's start with motion planning. Where are we today? In my lab, with some recent developments, we can do online motion planning for the robot that you can see here in a dynamic environment in milliseconds on a commercial CPU, okay, not a GPU, a CPU. So we are providing this kind of capability for a dynamic environment for any robot, okay, in any reasonable environment. So think about it, milliseconds. This did not come immediately, okay? This is the result of work that has been going on for many, many years. We started with tens of seconds, and now we are down to milliseconds and microseconds, as I will show you. The work that I'm describing here is based on a technique called sampling-based motion planning. And there are many sampling-based motion plannings. Work started in around 94, 96. I will not describe these planners here, but I will say that they sample the space somehow, and they create a structure, either a roadmap or the tree that they use for motion planning. You can read one of the 200 plus papers that exist on different versions of these sampling-based motion planners. Or you can use our OMPL, our Open Motion Planning Library. This is a library that my group is supporting for many, many years right now. We have we have about 4,000 users, 40 planners, 81 contributors. This is really a resource for the community. Last year, we showed how to take all these planners, the sampling-based motion planners, and have them work in microseconds in modeled environments. So what is happening here is that we can do, we can use a kind of parallelization called single-instruction multiple data parallelism and achieve kilohertz planning time speeds. What we do is that SIMD allows us to unlock several algorithmic improvements in the core operations of sampling-based motion planners. These are forward kinematics and collision checking. We always do that in a way that is really surgical, very, very careful, because these planners blend operations that are naturally parallel and sequential operations that can better be done in sequence. So we go down to the level of individual operations, and I'm talking about forward kinematics and collision checking, and we parallelize these, we schedule operations, and we exit as soon as we can exit to make sure that we get the best performance possible. So in a modeled environment, like I'll show you a comparison, our planner is in blue, plots are on a logarithmic scale, and orange and green are two comparison planners. We are orders of magnitude faster than what we had before. And if you look on the right, this is the quality of the path. It's the same quality. So we are computing the same quality of paths, only much faster. What is now very important is that because of the really common operation that we use, SIMD parallelism, we can do this on an Orange Pi. Okay, so on an Orange Pi, we on a single core of the ARM CPU, we are the times that we get are in milliseconds. Think about it, every robot having an Orange Pi and being able to do motion planning reliably, any environment, any robot. Now, what happens with dynamic environments? We can achieve this planning time, it works, but you have to be careful how you implement things. What you are seeing here is a camera. We have a camera on the top of this workspace, and you see the point cloud that we get from this camera. We receive a point cloud, we rebuild the scene representation, and we plan. In order to do this, we have to use SIMD parallelism, and we had to invent new techniques and new data structures, in particular the collision affording point trees. They allow us to do nanoscale collision checking, which enables us to plan in milliseconds in the environments that you see here. So this kind of operation is becoming very, very reliable and very, very fast and very, very cheap. This is what I mean by paying attention to operations that we use all the time in robotics, make them really, really good and get them out of the way, try to understand how to put everything else together, and everything else, as you saw, is already a lot. So the second thing that I want to talk about is the power of abstraction, modularity, and composition for long-range horizon planning. This is something that is not discussed a lot recently, but in my opinion is very important. So I'll show you an example. I will use the R2 robot of NASA. This is a robot that NASA designed for the space station. It needs to go from one end of the capsule to another capsule to the other end. It always needs to hold on a handrail. Otherwise, this robot will float in space, and this is not something that we want. So we plan under constraints, but we know how to plan under constraints. All right, we know how to do that, and we know how to do that fast and reliably. So in this example, we plan on this grain surface that I'm showing in the slide. All right, this means that the robot has one leg tethered to a handrail. When this surface interacts with the pink surface, we know that two different constraints are satisfied on the interaction, and we can move from one constraint to the other, which means that the robot can move to a new handrail and release the old one. And this is how we get the motion that you see here. It's no learning here, it's not complex, and this is the kind of behavior we are getting, and I can show you many examples. So this is compositionality of very, very simple operations, and it's done on the constraints. There has been a huge amount of work on long horizon planning, task and motion planning. It did not start with LLMs, okay, VLMs. It started a long time ago in 1990. And everybody since then has recognized that there are two very, very important parts when we talk about task and motion planning. One is the task planning, which is kind of discrete, and the other is the motion planning, which is the continuous part. All right. So we have a lot of things for each of these. You've seen in the previous talk for task planning, we can use VLMs, LLMs, VLAs. It is or formal methods or constraint satisfaction. It's a lot of tools that we have in our disposal, and these tools are becoming better and better and better. It's amazing, actually, what we can do. And on the other hand, motion planning, I showed you we can have motions that can be computed very reliably, or we can learn skills. I mean, machine learning has shown us how to learn difficult skills for the robot, skills that are maybe, require some dexterity or have other, let's say, characteristics that are hard to write down. The question is, how do you put these two things together? And this is where everybody is stumbling. And my opinion here is that you need to talk to think about abstractions. You have some task, okay, I'm talking about a long horizon task. You need some kind of representation of this task, some kind of diagram that has an abstraction of the task. You also need abstractions for the environment and the robot. We never talk about them, but it is the combination really of the abstractions for the task and the environment and the robot that give you what you see here on the right, some kind of a transition diagram that allows you to understand where you are with the task, what has been done and what has not been done. But in order to do that, you have to have operations that are composable. Okay, operations that can happen, that you can sequence in some sense, one after the other, and you know what you're doing. And in fact, these diagrams need to be weighted. So when you go through these diagrams, these transition diagrams, and you understand that you try to execute, let's say, a part of the task, and it fails, you have some way of understanding where else to go, how else to execute the task by the information that you have in these transition diagrams. And maybe we can construct these diagrams, maybe we need to learn these diagrams. So here is another thing that learning can help us with. And you need to deal with failed executions, because things are going to fail. And then what do? And maybe you need to learn behaviors, maybe you need to have things to do in the case that your planning fails. The thing that I want you to get from this is that, in my opinion, abstraction, modularity, and composition of operations that are reliable and fast can get us a long way. Some of these can be computed, some of these can be learned, but if you can compose them, then you win big. And now I want to say a few things about putting the human in the loop, because in the end, we want robots in the service of humans. Here's a video that I'm going to play, and look at the task. It's a very simple task. We want to build an arch. It has two black blocks as support, two white blocks as support, and it has a black block on the top. So here is the arch completed. What I'm going to do now is I'm going to replay this video, and I want you to pay attention to the human, okay, not to the task. You will see that first the human. Okay, let's hope this will start. Okay, first the human helps the task by correctly placing the black box. But here, it hurts the task by removing a block that was correctly placed. However, the robot needs to have a strategy, it needs to have enough information to complete the task. And these are things that I believe we are totally within our reach. But we need maybe to learn not to do the motions or maybe the reactivity of the robot. We can compute it with program synthesis, with constraint satisfactions. We have lots of tools with this. But maybe the human behavior. How would you deal with an adversarial human? How would you deal with a helpful human? How do you put that in context of the task that you want to solve? So I'm going to wrap up here by saying that I hope I conveyed to you my belief that we need robust and fast primitives in robotics, and we should continue working on these topics, either by learning or by traditional techniques. Compositionality is extremely important. I'm not surprised at all to hear about hierarchical frameworks for time, as in the previous talk. This is a must, in my opinion. We need to understand what to learn. Do we need to learn the motions? Do we need to learn the models so that we can compute any motion? Do we need to learn transition systems, abstractions, behavior? What is it that we really need to learn? And in the end, systems is both hardware and software, and they need to work together, and we need to display these capabilities for us to be credible. So I will stop here by thanking the students in my group who have done all this work, and also thank you for your attention. Thank you very much.
Good afternoon. My name is Kenneth. I'm the assistant professor in mechanical engineering, and I direct the assistive robotics and manipulation lab. And today I'm going to talk to you about robotic dexterity. I'll start off acknowledging all my amazing students who do so much amazing work, and they work very hard. So let's jump in. We've heard a lot today about robots that are operating in human spaces and how this would be extremely beneficial if we could actually have them in human spaces doing things that are useful. There's a huge market, a huge need for this. My lab looks at this very holistically. We want robots that can actually assist people. And today I'm going to focus really on the dexterous tasks that you really need for these systems to be effective in human-based environments. So there's been a lot of really cool work over the past few years and decades. But I think one of the key catalyst challenges is having robots that can actually manipulate their environment effectively. In our previous panel, we heard about the Roomba doing amazing things in the home, and then we really had this challenge, and I think it was Charlie that said, if you had a robot that could actually do manipulation, then you have that huge value for those things that you could do in the home. And the question becomes, we have manipulation, but is it good enough, right? We see a lot of these companies that come out and they use a lot of data, they can actually do a lot of cool things, but perhaps some things that we kind of take for granted, like if we want to button up our shirt, is still extremely out of the domain of robots right now. And why is that? So if I look at some of these videos that I just showed you here, there was challenges and lack of hand articulation. Maybe there's external cameras that need to be involved. Simple pick and place tasks are good, but if there's really dexterity that's required, this is still a really big challenge. And then suction cup is used on the industrial scale, but if whatever you're working with is not flat, hard, rigid, if it's soft and these other issues, you might have trouble. And also, how long does it take to teach these robots to do these things? If I think about teaching a person how to do these tasks, if they watch me and they feel these things, they're able to pick up really quickly. So why can't we close that gap for robotics? And if we think about the robots that we want working around us, the things we need them to do, the Roomba is a great example. You have the vacuuming. You have these social robots that are able to provide communication, home security. But what are we really looking for? I would argue we all recognize, and hence all of the humanoid robots that are coming into existence. If you had a robot that could do all of your chores, could look after an elderly relative, this would be the holy grail. So I'm going to jump into quite a few cutting-edge projects that we're doing in the lab. Some of them are published, some will be coming out this month, and really just trying to address this whole problem of manipulation holistically. And so I'll just quickly throw up all my students who work on all of these aspects of the arm and get into what each one of those components include. So one is the sense of touch. We need robots with a sense of touch that's comparable to what humans can do. If humans are going to teach the robots how to do this task, if the robot can feel what the human feels, then you have the data, the opportunity with that data to actually make the same conclusions the human would make with that information. So I'll talk about our novel sensor, optical tactile sensor, DenseTact. I'll talk about induction tactile sensing, which is a new tool that we're using in our lab that we think will actually lend ourselves to getting more efficient data from a person while still allowing them to actually have the sense of touch they need to perform a task. I'll talk quickly about our work in gripper hand design, how we can plan for how the hands should move using diffusion. I'll mention some upcoming work in JParse, where we actually figured out how we could actually move into and out of singularities with asymptotic stability. This is not damp least squares. This actually gets you to the point, and it helps solve an embodiment problem. If you actually want to watch a human demonstrator, you can truly follow their wrist location, their finger location, and I'll show you a video of that. It's a really cool paper coming out shortly. And then I'll talk a little bit about our work applied to teleoperation. Let's go. So, starting with design, DenseTact is an optical tactile sensor. You have a camera that looks through a translucent silicone gel. It's illuminated by LEDs. When you deform that extremely soft gel, you can actually see the shape and forces of the objects that you're touching. We use machine learning to take that image and actually output the shape and net force for that sensor. And right now, our version of our sensor is able to provide you a 6-axis wrench. We're going for a full stress field within the next month. Here's how we calibrate it. We push it into known indenters. Because we're so soft, we need to know where every position on the sensor is at once. And with that information, we can obtain the shape. And in this video, this is how we obtain the forces. We have a net wrench sensor, ATI sensor below that gets the force and correlates that to the image in our model. This video shows both the ability to detect the 6-axis wrench. So the ground truth is shown in green, our sensor measurement in purple. Same model, same setup. We can then use it to collect the high resolution calibrated shape, where for every pixel we have on the order of 0.3 millimeter accuracy per pixel on a megapixel image. What's next? So we want to actually be able to take this information and say, not only can we get high resolution calibrated shape, but what if I could give you the stress field as well at that same resolution and calibrated? If you imagine a person tying a knot, they might need to pull on the different strings and figure out which strings have tension, which ones are loose, and that's how they can actually do that when there's a collision from vision. Robots could potentially do this too with our type of sensor. And so this is the high-level method that we use to accomplish this. We say, well, we can build a version of our sensor in Abacus, we can perform these stress measurements, and then we can bring this over with transfer learning to the real world so that we can actually have a calibrated, high-resolution 3D 4-axis wrench sensor over the surface of our sensor in addition to the calibrated shape. We're working to miniaturize this because we're already thinking ahead of, like, what does it mean for industry to adopt these sensors? If they're too expensive for every finger, then that might make adoption more difficult. And so we're working to get a version that's under $30 and soon, hopefully, even under $10 per finger. This is what our current most latest DenseTact 2.0 Mini looks like. So here you can see our whole sensor. This one is under $40, and most of the cost here is actually in the camera. For a cheaper camera, you can just bring this down. And so what can you do with this type of sensor? So one is a task that is really challenging for vision. What if you wanted to reach into a bowl of screws, figure out which screw you're holding, and classify it? If you did this at Home Depot, you'd probably quit your job really quickly. Our robot can do this and save you a lot of pain and suffering. And so here you can see the robot reaching in, able to pick, sort, squeeze, and feel which screw is between its finger. If you try this with most other optical tactile sensors, you might struggle to actually feel the shape because they're too rigid. So DenseTact being soft can actually deform around the screw and give you that better classification. For the DenseTact Mini, we realized you could do things like tap grasping. If a person goes to pick up something that's really small, they actually use electrostatic forces to actually adhere to the object that they're working with. We were able to replicate that. We gave ourselves a rudimentary fingernail and could also pick up extremely flat objects as well, and we're working to integrate that into a more final design. And these have great statistical performances in picking these things up successfully. So moving to a more practical use case, you can imagine wanting to use these types of grippers in agriculture. So 2 questions. A, could you use the sense of touch to determine if you're squeezing too hard? And B, if you wanted to assess whether or not you were damaging the fruit, how would you effectively do that? So to accomplish that, we use DenseTact on our finger, and we compare this to the damage that would be caused by not using a DenseTact sensor. And we're actually able to show that using DenseTact in a diffusion policy, we're able to pick up soft fruits with precision and care. And how do we assess that damage? We actually use neural radiance fields. So we can actually take a Gaussian splat and scan a strawberry and use this to actually label areas of damage, which is perhaps a very nice emerging metric for actually fruit quality observation. Another use case might be using this to pick up very soft things like I mentioned before. So what if you wanted to pick up a cloth and figure out how many layers of cloth were between your fingers. You could rub your fingers together and use that friction information to tell you how many layers you were holding, and it turns out that this is a very effective method. What if you wanted to explore an object that might have been very dark or transparent or reflective? You can use the sense of touch combined with vision to, as you touch, to actually build a model of the object you were interacting with. So by touching this object many times, we can build a Gaussian splat, a statistical reference of where the surface is, combine this with vision, and then this allows us to actually build hyper-realistic views of objects that we're looking at. So here is a Gaussian splat that's combining both touch and vision. And if you just use vision, you have issues with the object being too dark, the surface being reflective or transparent, but with the sense of touch, adding that in, you're able to actually see these surfaces quite well. So another question you might ask is, well, if you're going to sense with these advanced sensing, what's the most efficient way to do this? And so we actually use next best sense, which says if I can touch the object or look at the object efficiently, I can determine what the next best position should be in order to effectively build a map of this object in real time. So kind of shifting gears here, so we talked about the sense of touch. What if I want to correlate this with what a human wants to do? I want to drive the system. What tools could I use for that? So in my work here done by Aaliyah Smith, she's using a HoloLens to actually view an arena and using those interfaces to actually drive the actions of the robot in a very intuitive manner. And so here she's able to actually pick and perform teleoperation using a digital twin of the object of the robot to actually drive and perform these manipulation tasks. And so this becomes really interesting if it's really hard to work at a robot at scale. Maybe your robot's really big, maybe it's in a dangerous environment, maybe there's a biohazard. How can you could use these systems to have a very intuitive way to actually work with a system, a manipulator, to control its desired motion. You saw a little bit of this as well in one of our previous talks. I think Dieter was mentioning this, but language is really emerging as a very powerful tool with VLMs to actually give these systems contextual understanding of what they're doing. So here we're actually embodying language into a Gaussian splat with affordances of the objects that we're looking at, so we can say, hey, if I want you to put the pot on the stove and put the fruit in the pot, could you actually achieve this efficiently? In the interest of time, I won't play this all the way out, but you can actually see how we can edit our Gaussian splat with that hallucination of what the person asked to be done, so move the pot to the location, and then with that plan, we can then execute this with the physical robot. Moving to that notion of arm control, it's been, even in the last talk, we mentioned like how you can actually use these sample-based planners to plan motions, but oftentimes those sample-based planners give you really weird motions that are not very intuitive. The alternative is to use things like a Jacobian pseudo-inverse. That works really well if you're in a high-rank pose of the arm, but the moment you move to a point that's near a singularity of the Jacobian, it locks up or creates a high velocity and you risk damaging your robot or breaking something. DSL, damp least squares, is a way to try to work around that, but it actually introduces errors so that if you want to actually reach a desired pose, you'll actually never really be at the position you commanded. So we address this with a new tool we call JParse. And I'll just show you two anecdotal videos here. The one on the left, I'm controlling a default X arm position control of the end effector to reach out and grab this cup. And on the right, I'm using our method JParse. So you'll see, bam, right there, the default Cartesian controller just stops immediately. And what you're seeing on the right is a closed form controller that is going all the way to the singularity with accuracy to perform a grasping action. This will be useful not only in controlling arms, but then if we want to think about embodiment for fingertips, I can say, where should my fingertips be? And even if your links are different than mine, now our robot bodies don't have to exactly match a human's body to learn. We can just say, where do we want the end effectors to be? And we can use this for both arm and hand control. So what's next? We want to keep adding on all of the sensor modalities to sensors like dense tact. What happens about vibration or temperature? How can we actually incorporate these into our sense of touch effectively? And if we want to do all the tasks that really matter, let's stop doing gimmicks and go for the really hard stuff that actually has market value. What does it mean to be able to do all of these things successfully? Part of that is having these capable systems and using all of the latest tools in order to know how we should effectively move our system to effectively accomplish goals. And some of the goals I think are worth trying are what does it mean for a robot to tie a knot when the string is actually pretty small, or zip up a zipper, or handle a tool with precision. I think if we can do these, we'll actually see a really meaningful market value for humanoids and all types of manipulators in human spaces. I'll end with this. How do we teach these systems? So I think learning from demonstration, imitation learning is a very powerful tool. Humans are fantastic instructors, right? We know how to do all the tasks we want our robots to do. So if you could actually put onto a person a pair of glasses so that we could see what they're looking at, if I could have you wear gloves so I know how your hands are moving, and if I could give you sensors on your finger that intercept your sense of touch without inhibiting you from feeling what you need to feel to do the task, if I could get all of that and replicate those abilities on the robot, then I think we would have very successful learning and quick learning with these types of systems. Thank you very much.